Good evening, everyone. I'm Ayushi Modi, the events chair of the IBPSA-Georgia Tech chapter. We as a chapter are organizing events like mentorship programs, educational lecture series, and symposiums to connect students with the world of building science. Cold Climate Housing Research Center, CCHRC, recently joined forces with the National Renewable Energy Lab, NREL. Overlapping research from the two organizations include whole building energy use, building energy system integration, health, indoor air quality, and energy technology design and deployment in extreme and rural environments. The MOO expanded CCHRC and NREL's research capabilities in circumpolar building science, government, industry policy, building design, and technical assistance. IBPSA Georgia Tech chapter and Cold Climate Housing Research Center with NREL are pleased to present a primer lecture series featuring Aaron Cooke and Stacey Fritz over the 2 days, 25th and 26th of May 2022. From this primer lecture series, today, the first lecture, Principles of Northern Design, will be delivered by Aaron Cooke. Aaron is a licensed architect and project manager at NREL's CCHRC in Fairbanks, Alaska. He manages the Sustainable Northern Communities program, which designs and deploys emerging building technologies and approaches in the Arctic and subarctic. Cooke's work primarily focuses on durable, affordable, healthy, and sustainable building design in extreme climates and remote locations. He works with architects, builders, technicians, local leaders, and tribes to design, build, and monitor innovative building across circumpolar north. Cooke has worked experience across the region with projects in Alaska, Canada, Denmark, Greenland, Iceland, Norway, and Russia, testing the new methods of building durable and energy-efficient homes in these regions. He has more than a decade of architecture and project management experience for CCHRC in rural Alaska. He has taught Northern Architecture and Arctic Engineering in University of Alaska Fairbanks, the University of Washington, and the Danish Technical University of Greenland. We welcome you, Aaron, and cannot wait to hear you about your views on the principles of Northern design.
Well, thank you, Ayushi. Can you hear me all right?
Absolutely.
All right. Do you prefer if I share screen, or do you prefer if someone else has the slides and I say next slide? What's the preference?
Tanmay will be sharing the screen, and you can just ask whenever you want to go next so that there are no glitches. That's all.
That sounds great. Thank you very much. Well, welcome, everyone. My name is Aaron Cooke. I'm an architect and researcher at the National Renewable Energy Lab's Cold Climate Housing Research Center campus in Fairbanks, Alaska. I'm going to talk today about an introduction to cold climate concepts in architecture and design. Almost the entirety of my career has been spent in cold climates. It's also where I'm from. I'm from Alaska. I grew up in a cold climate near the Arctic Circle in Fairbanks. This primer lecture is meant to be of interest to people that are that have already an interest in different effects of climate and different climate's effects on architecture and building, and it's also meant to be of use to students and practicing architects that already have an expertise in the temperate region or other climates and are interested in what it takes to build buildings in our climate, in the northern climate. Next slide, please. We're going to talk about the factors of our physical and cultural environment that might be different from most of the places that you have perhaps studied or designed. And really, this is a difficult thing to do as a designer, because chances are, if you're doing something completely new, like let's say building an ice road on the sea ice, and you need to learn how to do it, then chances are you've never done that before, and learning the best principles and best practices for designing an ice road is something that would start from scratch. Now, when it comes to designing buildings and housing especially, chances are you already know something about building houses and buildings, and so your task is much harder. You have to unlearn some of the best practices that are instinctual to you in order to design buildings that are appropriate for a northern climate. This comes all the way down to the way we talk about the land, the way we talk about the occupant, the way we talk about the weather, and even the way we talk about light. So we're going to start with light. Architects love to talk about light. It's an important part of building design. When we talk about light in the northern context, we're talking about a very different kind of light. And part of that is because at northern latitudes, the altitude and the azimuth of our light is significantly different than in other places, other regions. I know the majority of the audience here is from Georgia Tech and Purdue, or we have some audience from other members or other locations. But once you get to near the Arctic Circle, the azimuth of the sun, which is the horizontal angle that the sun takes over the course of the day, changes dramatically from the temperate regions and from the warmer regions of the world. Here we have a picture of Fairbanks, Alaska on the winter solstice, December 21st, and you can see that the azimuth, or the relationship, the angle of the sun's setting and rising on the horizon is significantly different than most places in the south. In the south, and we use the term south to mean the entire continental United States. I know that perhaps the people at Purdue would think that they're not in the same south as Georgia Tech, but to an Arctic person, you're all south to us. And so really when we talk about a southern approach to light or a northern approach to light, in the south, you know that the sun rises in the east and it sets in the west. And this is a simple thing that you've known since you were a child. In the Arctic and in the north, we know that in the winter, the sun rises in the south and it sets in the south, and it's only up for a couple hours. And in the summer, we know that the sun rises in the north by northeast and sets 22 hours later in the north by northwest. And that is a fundamental difference in the way we treat our relationship to the sun. Now, over the course of the year, next slide, please, we receive the same amount of sun as everywhere else on the Earth. We just receive it all at once, in the majority of it in a 5-month period, a 4-month period. So today, for instance, I think we've got about 20 hours of daylight in Fairbanks, in my hometown, a little bit south of the Arctic Circle. In December, we've got a little over 2 hours of daylight. If you added all the days together, we'd have the same exact amount of daylight as everyone else in this audience, wherever your hometown is. However, it sets and rises in different places, and also because of our northern location, the sun never reaches the same altitude. If you're near the equator, then you know that at noon on June 21st, the sun is almost directly overhead. It's almost at a 90-degree angle in altitude. And in the north, it pretty much never gets that high. It is much lower in the sky, even on the longest day of the year. Next slide, please. What does that mean? It means that our light is fundamentally more horizontal in nature than it is in most places in the world. The sun is not necessarily always overhead. It is out there somewhere in front of you in a horizontal relationship. Obviously, this is a small thing and it's a huge thing. It has an amazing effect on what we do with buildings. If you live on the equator, then you block the sun because it's too hot, but you block it through your roof. If you're in the temperate regions, the mid-latitudes, then you filter the sun so that you get it when you need it in the winter, and you block it when you don't need it in the summer. But again, you're blocking it and filtering it through your roof, through a horizontal surface, working against or with a vertical design input. In the north, we try and capture the light, but we do it through our walls. We don't do it through our roof. We do it through vertical pieces of architecture. And this has huge implications on very simple things about what a building should do, how it should behave, and what it should look like. Next slide, please. It also makes daylighting very difficult. This is a school based in, I think it's either in Iqaluit or in Iqaluit in Nunavut, and it is a very warm building, but daylighting is very difficult in a place where the sun is only up half the year and where the sun is coming at a horizontal angle instead of a vertical angle. Next slide, please. If you're in architecture school, you've already seen a diagram much like the one on the screen right now. It's a basic daylighting diagram. It's a basic passive solar gain diagram. It's 101 level stuff for coursework in architecture and design. To calculate a proper overhang, you take the angle of the sun on the summer solstice, the one that you're trying to block. You take the angle of the sun at the winter solstice, the one that you're trying to capture and allow light to enter deeply into your room. And you calculate between those two an overhang in a horizontal dimension that'll allow you to capture the winter sunlight and block the overheating potential of summer sunlight. So this is something that we already all know how to do in architecture school. Let's bring that to a northern context with everything we've just learned about the quality of northern light. Next slide, please. If we were to take the same process of creating an overhang based on blocking summer sun and allowing winter sun in, those overhangs would be incredibly unmanageable and structurally unbuildable. And that's even before we handle the snow load. So our best practices that we've already learned, they don't work in this new land. They don't work the farther north you go. So we have to think differently about the way that our buildings are going to allow for daylighting and for blocking of sun. Because if in the winter the sun rises and sets in the south, then there is virtually no reason to have windows in the north side of your building. Northern light is much coveted in architectural circles, in warm places and in hot places. It's a nice base, cool light. It's always been the best light for artist studios, for architecture studios. You don't worry about overheating. In Alaska, in the winter, when you need the heating the most, you'll get no light from the north of any kind, unless it's refracted off the snow. Northern sides of buildings are just places where you leak heat. They're good places to put windowless areas, bathrooms, loading docks, server spaces. Next slide, please. Additionally, if you're thinking about energy production, then we're thinking of new ways to treat this northern sunlight as well. If you want summer sun for solar PV, you're much more likely to make those, if the sun is hitting your wall more than your roof, then that's where your PV belongs. If your sun is never going to get to the angle that it does in the temperate region, then the more vertically angled your solar PV is, the better. Additionally, if you're getting most of your summer light in the summertime, where we have a high azimuth for our light, then an eastern and western face of the building may be as good as worth the investment, not only the southern face of the building, because we're rising at 3 in the morning in the north by northeast, and we're setting at midnight in the north by northwest. That's plenty of time for the sun to hit your western and eastern focuses of your building. There are other reasons that you see this. Next slide, please. The conventional wisdom is that the best orientation for the most efficient solar production for electricity is the latitude plus a certain amount of degrees. But once you get above 60 degrees latitude, the difference in efficiency really is negated by simple things like snowfall. So here we have an arrangement of solar panels where 4 of the solar panels are put at what math would tell us is the optimal angle for getting the most electricity out of the sun. The one in the foreground would be considered less efficient mathematically for the amount of solar radiation that's going to get. But that only depends on how many times your maintenance staff is willing to go out and shovel off or sweep off those more efficient panels. And so these types of inputs are things that northern designers need to think about. Next slide, please. Same goes for buildings that fail to appreciate our northern light. This is a building in Greenland where it was built by a Danish company in Denmark. They love their skylights. Denmark is a wonderful place for skylights. They don't work very well in Greenland. Generally, they leak heat. Generally, they're still thinking like Southern people, like Southern designers, because you can see that the light, you're poking a hole in a roof, and if you look at the blocking and the opaque privacy screens in front of the walls on the terrace, you can see that there's a misunderstanding of where the light is coming from. That we're in a place with horizontal light instead of vertical light. So this building seems out of place. It's in a northern place, but it doesn't look like a northern building. It doesn't behave like one. Next slide, please. By contrast, this is another building in Greenland that seems to take into account the uniquities of northern light. Although there is a place where they're trying to get high light in, they're understanding the horizontal nature of that light. They're also understanding that light wrapping around from the south to the west portion of the building. Next slide, please. Here's a building. It's a dormitory building. And when I look at a building like this, I think to myself, at least in terms of light, now we're thinking like northern people. This has solar thermal array on the building, but the solar thermal array tracks the natural azimuth of the sun in the summer. It goes all the way from the northeast to the northwest, so that it can be getting warmth and hot water for the full amount of the sun's horizontal traverse across the horizon. It is also on the roof, but it's in a near vertical position so that it's able to get that horizontality of light. And the rest of it, the rest of the building looks warm. It looks fortressed against what is obviously a physically antagonistic environment. I think this looks like a building that belongs in the north. Next slide, please. So now we just spent 5-7 minutes talking about how we have to relearn everything we thought we knew already about light. And we're going to have to go through this exercise in a primer lecture about northern design for land, for warmth, for any other of things that we already knew quite a bit about that we need to unlearn. So we're going to move on from light to land. We're going to talk about the way that the Arctic specifically has a relationship with land. The fundamental way to think about the land in the Arctic is that it is inverse to the way that temperate and southern peoples view the land. Even if you live in a place with a winter, even if you live in a place with a cold winter, it is likely that you know deep in your heart that the default status of the ground is warm, that even on the coldest day of the year, if you took a shovel and you dug through the frozen ground, if you dug a hole deep enough, you would eventually get to thawed land. As an architect or as an engineer, that means that the way you design buildings is you design your foundation to predict the depth of that winter frost and get underneath it, so that your foundation is always on thawed, warm land, because that's the way the Earth is supposed to be. In Alaska, we know, and in Russia, and in northern Norway, and in Greenland, and in northern Canada, if you grow up in the Arctic or the subarctic, you know deep in your heart that the Earth, its natural state is frozen. It's supposed to be frozen. That's the way the Earth is supposed to be. That even in the deepest, hottest day of summer, if you dug a hole with a shovel into the ground, into the mud, eventually, if you dug deep enough, you would come to frozen ground, to the way the Earth is set, its default setting. This is a simple thing. This is an important thing. When we talk about permafrost melting, when we talk about climate change in the Arctic, and we talk about damage to infrastructure from climate change, think of that inverse relationship of warm ground and cold ground. And think of how much damage would occur in your hometown if every piece of ground that you knew was supposed to be thawed froze overnight, with all the water and sewer in it, with all the electrical infrastructure in it, your bridges, your foundations. And that's why people in the Arctic are terrified about the melting of the permafrost, because our land has been frozen for 10,000 years and it's thawing in ways that we can't easily predict. And that is going to have incredible, devastating effects on our infrastructure and our buildings. As you can see, there's a location of 184 small villages affected by increased flooding and erosion, and that is directly tied to warming climates and the destruction of the thermal regime of the soil in our region. Next slide, please. So how does that affect our land? Well, for one thing, it inundates it, because all frozen ground, when it melts, releases its bulk moisture from ice to water, and that has unpredictable effects. So flooding and sinking are things that we deal with. Next slide, please. The other thing it does is it causes unprecedented erosion. Much of the western coast of Alaska is set up like a big frozen bayou. If you imagine the southernmost part of Louisiana and that landscape, most of our western coast looks like that, except it's been frozen for a very, very, very long time. As it melts, it is unable to maintain a shoreline against the sea. And so in some of the towns where we work, we lose up to 80 feet of shoreline every single year. I've been working in a community in Newtok for the last 15 years, and in that time, I've seen 4 football fields worth of shoreline go away. If you live near a coast, think of how much 4 football fields of coastline feels like. It's an incredible amount of damage. It's an incredible amount of trauma. We have a number of communities that are forcibly relocating as we speak because there's no time left to move. And so that our relationship to the land is changing. And it's changing primarily because of this melt. Next slide, please. Next slide, please. We talked a little bit about how buildings meet the ground. If you need to get below the frost layer in the southern latitudes so that you can stay on stable ground all through the winter, then for us, we need to drive piles and reach the frozen ground so that we can stay stable through the summer. If we're unable to do that, then quickly the ground drops away from our buildings. Both the buildings in this photo started off 18 inches off the surface of the ground. And in less than 10 years, both of the ground underneath these buildings, these are both in the northern part of Alaska, has melted. When it melted, all that ice turned to water, flowed away, and we see subsidence of up to 8 foot in less than a decade, which is an incredible amount, an unprecedented amount of subsidence that we're dealing with our foundation design. This is important. That's not to say that all of Alaska and all of the North has permafrost soils. And so it is important, for instance, if you're on the student teams that are designing for a community in Alaska, if you're designing a foundation in the North, the first thing you ask is the ground frozen? And the second thing you ask is it supposed to be? And that determines your foundation. You don't want to make any assumptions about the thermal regime of the soil. But if your first question when you get a new commission is the ground frozen? Now you're thinking like a northern person. Now we're thinking like northern designers. It's an important part of how we approach a site. Next slide, please. I'm going to show you a couple experimental foundations. These aren't things that I am going to present as best practice because I'm in research, and so we're supposed to be pushing new types of foundations. So the foundations I'm going to show you here are not necessarily typical, but they are things that we're working on to try and appeal to the level of change that we're undergoing right now. This first foundation is in a village called Mukhtavik, which is being moved. It's a village of 280 people that is being relocated as their village falls into the sea from coastal erosion based on climate changes. The problem with moving 280 people across a bay to a new location is that there's no time for platting and subdivision planning and surveying. And so the houses don't have a site. There's not enough time. So we had to create a foundation that was movable on skids. We created a rigid foundation of a space frame that's on skis that could be built during the short summer seasons and not have to worry about being held back by administrative issues. Once the new town is platted, this house can be towed or was towed to its plot. You know, with as many difficult issues we have with our physical environment, worrying over the permitting and legislative environment is not a luxury that we have. And so there's kind of an urgency to the way we design foundations. Next slide, please. And the people we like to test the more risky foundations on are ourselves. This is where I live. I live in a little group of 4 buildings called the Sustainable Village at the University of Alaska Fairbanks. We designed them specifically because the land is 31.5 degrees and ready to thaw. When that happens, no insurer, no bank, no developer is going to touch this land, and it's in the middle of town. And so how do we deal with the changes that we're seeing in our landscape? So what we did was we built these 4 houses. I live in the one in the top left, the yellow one. You can see University of Alaska in the background. We tested these houses with various different foundations, some of them more conventional, some of them a little braver, to try and see what will happen when that land inevitably thaws. And then we put thermistors down in the land 30 feet so that we're ready when that happens. Next slide, please. So in the house I live in, we basically built a foam raft foundation that we're hoping can span the land when it finally melts, while simultaneously buying us some time to keep the melt from happening. So we've got over a foot of foam insulation married into the network of lattices. You can see that that's steel framework. Now, if you're thinking, you know, about design and you've taken your thermodynamics course, you're thinking, why the hell are they using steel? That's a great conductor of heat. And we're going to talk about that a little bit later. Next slide, please. This is the research center itself. It's the northernmost campus of the National Renewable Energy Lab. They have a couple campuses in Colorado, one in DC, one in California, but this is the Arctic one. It's on terrible land. It's on land that is fractured schist and less silt, and more silt than anything else. And it was cleared at one point, and the began to thaw. When land thaws, it does unpredictable things, we have found. What we did was, because it's a large building, it's 20,000 square foot, you can see in the bottom portion, we excavated what looks like a pond, but really what we did was we excavated the mass of the building and we put it on the site for 2 years to overwinter to see how the land, as it changed its thermal regime, would handle the load of the building. We were able to make some assumptions based on that data. Next slide, please. That's not really enough, because a couple tons of dirt on your site before you build the building isn't really going to tell you exactly what the building is going to do. And so what we did was, after that, we super insulated the foundation, but we also mechanically separated the spread footing from the grade beam of the foundation. And what does that look like? Next slide, please. It means that in each pilaster, we have a plenum where, if need be, and the ground starts to really change and melt, we're able to jack the foundation and move the building. At 20,000 square foot, I believe this is the largest adjustable foundation in the Arctic, in the north. And for better or worse, we haven't gotten to test it yet. You know, half the crew here is pretty proud that we insulated it enough that we're still on stable soil, and the other half is getting pretty impatient that we haven't had a chance to test this new toy and see if we can adjust a building this size. And that's what research looks like, you know, waiting for disaster and then getting impatient if it hasn't come yet. Next slide, please. So we've talked about light, we've talked about land. This is probably the least surprising one. In the north, we always talk about heat. Heat is king. 80% of our energy load is heat instead of electricity. When you live in a place that is cold enough to kill you, you care about your heat more than you care about your light from an electricity and power standpoint. The interesting thing is, all the animals that thrive in the north, they don't eat more fuel. They don't eat more food in the winter in order to stay warm. Northern animals grow thicker skin. They grow blubber, they grow fat reserves, they have thick coats. They don't just eat more. And yet, for most of my lifetime, the way that the design industry has treated northern buildings is to have thin walls and just feed them more fuel. It took an embarrassingly long time to rethink that. And it is being rethought now, but it's late to the game. Generally, a northern wall or a northern approach to heat, a northern building should have thicker skin, unless you're using something like vacuum insulated panels or aerogel or some of these magic materials that we rely on or hope will come into the industry for us. Until those times, a northern wall is a thicker wall, and it's a wall with a thermal break. It's a wall where nothing that's touching the inside of the building is also touching the outside of the building and forming a bridge between the cold of the outside and the warm of the inside. Next slide, please. So we are focused, always focused on reduced demand. Some of the greatest technological innovations of our time right now are on more intelligent supply. We talk a lot about what's been done in solar energy. We talk a lot about what's been done in certain technologies like heat pumps, geothermal. It feels like every half decade, the supply is making leaps and bounds over what it was when I started my career. Demand is lagging behind. We should be reducing demand and putting as much effort into reducing demand on our buildings as we do into making a more intelligent supply of heat and of power. So that is an emphasis. And as an architect in the north, you'll never get away from that emphasis on reducing our demand through our building envelope and through our insulation value. Next slide, please. And this is what that looks like on a construction site. We're looking at a lot of petroleum-based polyurethane, bad for the environment materials that we're used to using to get our thick coat on our walls. And that's really where the next the next jump needs to be made is if we need a thick wall, what are we going to make it out of that has some presence in the circular economy, has some ability to go back to the earth? Because right now, out of desperation, we use a lot of pretty bad stuff to keep ourselves warm. And I think that's something that is where we need to go next. If half the R&D went into the demand side that it does on the supply side, we'd be doing all right. And that's, as young designers, as people getting ready to start your careers, if you're interested in being someplace exciting, then the demand side of envelope and the way we do envelopes in buildings, that's an exciting place to be positioned. Next slide, please. And it's not all chemistry and rocket science. Some of it is really simple stuff. A northern building will leak less heat if it has more volume as a relationship to its surface area. This is simple geometry. It's something that we need to think about as the first principle. If we're a northern designer, if we're thinking about designing it, or even if we're a southern designer, designing a building for a cold climate, half our job could be done with geometry, thinking about what is the surface area to volume ratio of our building. That is the easiest. We don't say low-hanging fruit in Alaska because it's too cold to grow fruit here, but that's the easiest, simplest thing to get at first, is what is the shape of my building? Next slide, please. These two buildings are one high school in Anchorage, Alaska. The bottom right building is A.J. Diamond High School. It's the high school I attended a long time ago when I was a student graduating from high school, and it was eventually replaced by the building to the left of it, which is the new A.J. Diamond High School. I was lucky to catch this Google Earth shot when they'd completed the new construction before they tore the old building down. This building was a terrible building to go to high school in. It was designed by a California firm, like a California high school, in the Alaskan environment. It's a campus-style high school, single-story buildings, incredible amounts of the surface area to volume ratio, very little volume of heatable volume compared to the amount of skin necessary for this building. It was cold, it was damp, it was a terrible place. The building on the left looks more like a northern building to me. It is compact. It has a lot more volume in relationship to its surface area compared to the rest of the building on the right. And it looks like it belongs in a northern context. These types of things do not take fancy wall sections. These are simple ways of looking at space, looking at warmth, and looking at a building not just as a place that you occupy, but the thing that keeps you warm and keeps the outside out and the inside in. Next slide, please. So thermal bridging and detailing is something that comes into play here because not only do we want to limit our surface area to volume ratio, we want to make sure that in key places like inside corners, in our stair platforms, in our building plates, our floor plates, how are we going to insulate those? How do we wrap a coat around the parts of the building that are supposed to tie our structure together? It creates a new way of thinking about structure. A northern way of thinking about structure is that all of it happens inside the coat. If you've ever designed a curtain wall, that is the opposite of the way that you're used to thinking about buildings. Generally, the structure happens on the outside of the thermal layer. So again, and if you're sensing a theme here, I think it's something that is meant to be obvious. Fundamental things that we know to be true are opposite when we get to a place that gets to 60 degrees below zero in the wintertime. And those fundamental things that we think we know are probably the most dangerous things as we move and practice in a new place. If I were practicing in the desert, I've never spent much time in the desert. Chances are I'd make some pretty elementary mistakes from the point of view of a desert person, because all of my thoughts of what a building's supposed to do are based in someplace far, far away. Next slide, please. So we can do more intelligent supply. I know that some of the people on this primer lecture are hoping to design a building in Cooke Inlet in Alaska. Cooke Inlet is a great place for all types of supply. It's probably one of the most energy-rich basins in the world. It's got some of the biggest tides in the world. It's got big winds. It's got interesting solar. It's got geothermal volcanoes. It's even got oil platforms. If you can run a motor off it, it exists in Cooke Inlet. Now, this idea of intelligent supply is, I think, an interesting one in places like that. In much of the north, we have less options. In the top right of this picture, what you can see is just a giant, looks like a blue tank. That's a 20,000 gallon tank that we charge with hot water in the summer. This is an experiment of creating a thermal battery. The idea that we can use heat from one part of the cycle to another. If you live in Arizona and it gets very hot during the day and very cold at night, it's pretty easy to use the heat of noon at midnight. You just need to somehow store it for 12 hours. It's a lot easier to use the heat of noon at midnight than it is to use the heat of June in January. And that's really the problem that we have in the north, is how do we store heat from the summer when we don't have much need for it, but where the sun is up all the time? And how can we store it for 4, 5, 6 months? This is an interesting thing to work on from a thermal battery standpoint. Next slide, please. So going through this pattern, we've been talking about light, we've been talking about the land, we can talk about air. Arctic peoples have the highest rate of respiratory infection in children and elders in the world. And it's not because this is a traditionally humid place. It's because we spend quite a bit of time indoors, and because the building physics of moving air and moving fresh air in a cold place are extremely complicated. And if not complicated, at least daunting. We have a pretty terrible amount of mold in our buildings in the Arctic, and that's not just Alaska, that's everywhere in the Arctic. And there's a specific set of reasons why that happens. Next slide, please. One of the reasons is that if you're in an economically depressed community, you're more willing to pay for heat than you are for fresh air. If you don't have good heat, you can feel it. If you don't have fresh air, maybe you can smell it, but you can't see the things off-gassing from your furniture. You can't automatically feel the health, the problems with health that come from breathing bad air. So in economically depressed communities, it's very common for people to sabotage their own indoor air quality to save on their heating bill. And getting around that can be very difficult. It leads to mold, it leads to a lot of pretty terrible things. So we're always trying to recover heat through our mechanical systems, heat recovery ventilators and energy recovery ventilators, things that allow the outgoing, all that wonderfully warm, terribly dirty outgoing air. We want to steal that energy and give it to our wonderfully clean and terribly cold incoming air. And from an engineering standpoint, that's no small trick. That takes some doing. Next slide, please. So if you see things like mold in a northern house, if you see things like weeping windows, it's generally not a problem with the wall or the window. It's more often that we're underventilating, and underventilating is something that's very common here. Next slide. The key then is to marry our fresh air to our warm air. If the air that you need that's warm is also the air that you need that's clean, then you're never going to turn it off. And so we spend a lot of time thinking about how to marry fresh air and warm air with our mechanical systems. And if you're an engineer, if you're an architect, this is an interesting idea. If you're an engineer, this is an exciting problem to work on. Because we don't want the problems someone's already solved. What fun are those? We want new problems to solve, and here's one. If you can figure out how to make your warm air your clean air in a very cold place, then you're going to be doing important work. You're probably going to make a fair bit of money. It's a field that is it's still in its infancy, and I think it's something that's worthy of inquiry. Next slide, please. The fundamental thing that I think causes the most mold in northern structures is a misunderstanding of dew point. Dew point occurs everywhere in the world. It's that temperature at a certain humidity when the gaseous moisture in the air turns to liquid. If you're in Georgia or Indiana on a hot day in the summer and you have a cold beer or a cold can of Coke on your table, it immediately starts to gather water because it's cold enough that it all the moisture in the air, the humidity in the air condenses on the surface of the can and starts to create it wet. Wonderfully refreshing if it's a beer, terrible and catastrophic if it's a wall. If we don't understand how dew point works in northern context, we run a risk of rotting out our walls. And so fundamentally, the most important thing is that dew point is reached outside of the portion of the wall where it can cause damage. If you look at this graph, if it's 60 degrees below zero outside and it's 65 degrees above zero inside, somewhere in this cross section of that wall, dew point will be achieved. There will be a time where there is the temperature for whatever humidity is in the house to condense. So what you need is to create a wall system where that condensation can't occur. Seems difficult, but condensation needs two things. It needs dew point, a certain amount of humidity, and it needs a condensing surface. And it needs the movement of water, vapor. And so we spend a lot of time thinking about how to keep water vapor from moving through a wall. A lot of time thinking about how to eliminate condensing surfaces from within our wall. Next slide, please. And that's easier said than done. And Alaska is a big state. The Arctic is a large region. So dew point calculations are down to the city. They're down to the latitude. They're down to coastal versus interior. If you're designing a building in Alaska, there are a series of dew point calculators that are down to the town, where you can decide how much impermeable insulation needs to be on the outside of the wall versus how much on the inside. And I'd encourage you, if you're actively involved in the design of a building, to get to know these dew point calculators and use them as much as you would any other tool in your softwares. Next slide, please. One of the things that dew point is also important is because we have significant amounts of air leakage in cold climates. Stack effect is the idea that cold air will sink and warm air will be more buoyant and rise in any building. This isn't unique to the north, but the bigger the difference between your exterior temperature and your interior temperature, the more forceful stack effect is. So that a 4-story building in a place like Washington, D.C., and a 4-story building in a place like Fairbanks on a day when it's 40 below is vastly different. So you have incredible pressures, positive pressures on the inside of our ceilings. And you have incredible negative pressures at the base of our buildings. Next slide, please. How do we handle this? This is the Russian approach. This is a building in Arctic Russia. You can see that it looks like it's built on the ground and that it's not particularly worried about stack effect. But if we tear the skin off, next slide, please, we can see that the entire base of this building is false, that it's not actually the base of the building. These giant, very expensive concrete members are lifting the building up above the permafrost so that the finished floor is over 2 meters off the ground. And it's doing that for two reasons. It's understanding that stack effect is going to be intense in this incredibly cold environment. It's allowing that negative pressure to come into the building, all that cold air, and then putting your insulation above it so that then the stack effect is not as damaging from a standpoint of heating. It also has an added benefit of keeping the ground frozen, because as we remember, the default status of the Earth is supposed to be frozen in this community. And so they're trying very hard to keep it that way. Next slide, please. When we fail, you can see it. If you design a building that hasn't taken stack effect or pressurization or dew point into effect, you can see it in the roof, you can see it in your structural members, you can see it in your walls. It rots quickly. It is very unforgiving. Nothing fails small in the Arctic. Things only fail big. And so when you have like an oversight for a detailing, it's not going to be a small problem of detailing. It's likely going to be a fairly significant one that you'll be able to visually see rather quickly. This is good from a repairs and modification standpoint. It's bad from a cost and liability standpoint. Next slide, please. So we anguish over vapor open and vapor closed walls. We anguish over whether or not we should be allowing diffusion through our walls. It's not really correct to say a house breathes, but, for lack of a better word, is the house supposed to breathe? Is it not supposed to breathe? That's not an easy answer in a cold climate. Depends a lot on humidity. It's a level of expertise that takes a long time to ascertain. If you're designing buildings for a cold climate, it's a good idea to have a consultant that this is all they do. This is all they think about is diffusion and air leakage in cold climates. Next slide, please. And our vapor barriers have been our traditional way of handling that. Wrapping the entire inside of the building in plastic on the warm side of the wall. That's been the best practice for most of my lifetime. There are probably better ways to skin that cat, but so far that's still what is most common. It's skilled labor. It's not something that can be done by just anybody. It's something that you should definitely schedule into your inspection regimen. A contractor should always know that you want to inspect the vapor barrier once it's finished and installed, but before the interior sheathing goes on, and then the proper attention goes into it. Next slide. Anybody want to enter in the chat what they think this is? I'd be interested to know if anyone has a guess as to what this piece of equipment is. Barring, I don't see anyone jump into the fore here, which either means no one knows or I've put you to sleep, but I'm gonna tell you that this is where you keep the poop. This is, if you're in a village with permafrost and no water and sewer, then someone in the family's job is to take a bucket full of your human waste and walk with that bucket in hand to this receptacle, pour it in by hand. Usually it's a kid, and then someone comes and picks it up and brings it to a lagoon. And that is another pretty big problem in Arctic regions. Next slide, please. The alternative for most of my lifetime to that bucket, we call it the honey bucket, is this: a water system, a sewer system that is above grade, because remember, the ground's frozen. We can't put it below grade. It's above grade. You've got to drive over it. You've got to put bridges over it. It's a line that everyone can see. It's a line that's out in the elements and has to be mechanically heated so that it doesn't freeze, and it goes to the treatment plant at the edge of town on top of the tundra. And that greatly affects the way that you handle your infrastructure. It affects the way you do your town planning. You can see the quote on the bottom left of the screen is from a public meeting that we were at, where sometimes your water and sewer is the prime determinant of where you can develop at all. And that's crazy, but that's still where we're at. The idea, well, there are many places in the Arctic that still don't have water and sewer, running water and sewer. We're still using buckets and we're still hauling water from the river, which is crazy because, the Romans and the Chinese had running water thousands of years ago. But those are southern aqueducts. I think it's no mistake that the idea that you should defecate in the same place that you sleep was invented in the South, because no northern person would have ever invented that. I think that it's an assumption that we make about the way that houses work and the way buildings operate. If our primary concern was keeping that thawed enough to get it someplace safe, then we wouldn't set up our infrastructure in a linear fashion. We'd be doing something different. Next slide, please. So these are systems that think more like the northern context. We have site-based single-family sewage treatment plants, as opposed to trying to run pipes all over the tundra above in the cold to get to a centralized sewage treatment plant. Now everything, if we come from an urban area or a southern latitude that we've been taught is that centralization increases efficiency, but only above zero. Centralization does not increase efficiency below zero, and so, or not necessarily anyway. And so many of our approaches to infrastructure need to be point source if we're able to build buildings that will work in our physical environment. So this is a house-based sewage treatment plant. Next slide, please. And this is a water treatment plant tied in, or a water purification plant tied into a sewage treatment system for a northern context. And basically what we're doing is we're imagining delivered water, and we're imagining treatment of wastes on site in a way that it can be at the scale of the home, the scale of the building, instead of the scale of the village or the community. And this is a very different way of looking at infrastructure. Next slide. This is probably the least surprising to the audience. We deal a lot with snow. Snow is a formidable issue in northern design. If you're designing for a community, we've already talked about how you should ask if the land is frozen or if it's not. We should also ask if snowdrift is a problem. In much of Alaska, snowdrift is a prime design constraint, and it routinely buries buildings in communities that get less than 24 inches of snow a year. Snow is vector transport of particles. So when you think of snowdrift, think of it like sand dunes. It doesn't matter how much sand there is. It matters what the wind does with it. So when we think of snowdrift, we don't think of, oh, it snows a lot in this area, I bet there's worse drifts. What we should be thinking is, this is a windy area. The amount of snow from a calculation standpoint is considered to be infinite. So the wind is really what we want to track. How much snow is moved around. Next slide, please. And that is more or less predictable. On the leeward side of a building in an area prone to snowdrift, there will be a scour zone roughly equal to the height of the building in front of the building on the windward side. On the leeward side, on the far side of the building, the part sheltered from the wind, the snowdrift can creep to 10 times the height of the building, and it can bury the entire building on the leeward side. If there's any rafters or river hounds here, it's a lot like eddies in a river. When you're in the fastest channel, it's clear because there's not as much in suspension. It's moving fast. When you go out to an eddy, that's when the sand and the silt and everything gets deposited. Snow is no different. As soon as we find shelter from the wind, the snow finds a shelter as well. And so an incredible amount of unnecessary diesel fuel is used to dig buildings out. It's a place where we could do better as designers. Next slide. If we don't consider wind orientation and snowdrift, we get moments like these, where our front door is basically exactly in the tail of the snowdrift. And that can be, as an architect, pretty embarrassing. As an occupant, it could be pretty infuriating because this is a lot of energy that needs to go into clearing this entrance for fire egress, for entrance, for basic usage. So this is not an asterisk, this is a prime determinant in many regions of the state. Not every region, so just like when we talk about permanently frozen soils, one of the first things we should ask is snowdrift a design input for this region? Next slide, please. Same goes for trying to handle ADA compliance. Now, if you first saw this picture, you might think that this is a lazy maintenance person and they just haven't been keeping the ramp shoveled clean. But this is on the leeward side of a building. It wasn't taken into account, the snowdrift. So after every wind event, the handicap ramp would be completely buried in snow and unusable. And it's difficult enough to have mobility issues in the Arctic without also dealing with this. So thinking about accessibility, thinking about universal aspects, universal access to our buildings is different in a cold climate. Our buildings are up off the ground. We're dealing with snowdrift. We're dealing with different things. And so it's something that we need to consider in our design. Next slide, please. And so this is, again, what I think, this looks like a northern building. They have an understanding of the elevation the building needs to be at. They have an understanding of the vulnerability of the access ramp. They put it in a place where people have universal access to this building summer and winter. And that is, I think, what we're going for as designers is that understanding of seasonality. Next slide. Now you could handle snowdrift completely just through geometry. This is a research station in Cambridge Bay, I believe, that basically is optimized for snowdrift. Go ahead and next slide, please. So it was created specifically because it was going to be deployed in a place that buildings were routinely buried by snow in the region. Not that there was that much snowfall, just that it was a very windy place. So you can see in plan there was a great deal of effort that was put into the aerodynamic nature, the raised floor nature, and the structure of this building so it could never get drifted in. Everyone was very proud of it. It was considered a success, but it has, as an architect, I can tell you that it has problems finding tenants, because would you want to live in this building? You know, that's a question. There's one thing to handle the physical environments, but there's also the cultural and the way that we use space. Sometimes those don't line up nicely. And so it's important to think not only in terms of the physical parameters that we're trying to design for, but ultimately buildings are for people. At the end, you want a building that people are going to want to occupy. It's not merely enough to be able to respond to the physical parameters of the environment. Next slide. Thanks, Michael. So these are buildings that take snowdrift as one of their primary design constraints, but are meant to be occupied. It's the National Parks building in Kotzebue. It's a recreation center and gym in Utqiagvik. Buildings that know that they are big, they have large footprints, they could easily be buried in snow, and so they design themselves almost like the prows of ships going into the wind. Handling snowdrift is a primary design constraint. To my eyes, they look like northern buildings. They look like they belong. If I saw this in Seattle, I'd think that was a pretty weird looking building. But that's part of what we're trying to conclude here, is that the issues that we're talking about are not aesthetic issues. Our aesthetics and our program come from a northern adaptation to life, to our climate, to our culture, to the way that people live in a northern aspect. And so if you want to design in a northern place, those are your primary design constraints. That's the best place to start. Next slide. This is a house that we built in a small community. It's an experimental house. It was meant to be a low energy home in a community called Quinnahock. It's a couple hundred people, 800 people, I think. They're having enormous snowdrift issues, routinely burying the entire town. And what we did was we did an analysis of creating what an octagonal structure might look like. We put the entryway on the southeast portion of the building because that's where the prime wind was coming from, so that it could lean into the wind like a bison or a moose. And basically every time you started to turn a corner on one of these 45 degree angles where the snow would start to deposit, you would turn the corner, it would speed up, and you'd be able to self-scour the building. Go ahead and go to the next slide. The first winter was a great success. It's not a great picture, it's from a cell phone a while ago, but you can see it looks like it's been shoveled around the building, but actually that's just wind action. That's just geometry. Through the geometry of the building, we're able to self-scour and keep all that snow away from the building. We had an unintended consequence in that we had some frost heaving at the foundation. It was an unacceptable level of frost heaving, so I came back the next summer and we layered earth up against the building to try and buy us some time from an insulation standpoint. Next slide, please. So you can see the first winter there, and then the second summer we put about, it wasn't even 24 inches. It was like 18 inches of earth at the base of this wall, trying to keep the foundation from melting the permafrost and heaving or slumping. So next slide. This is the second winter. Just changing the ground 18 inches, we were burying the building again. This is not much of a margin for error, right? We went from scouring the building all the way in plan to completely burying it just by handling a separate problem. Often our solution in architecture, this is not going to be news to folks in the field or studying. Often our solution to one problem creates a secondary problem, and that was what was similar. And I'm glad I'm in research because this was very exciting. This is a wonderful failure. We were very excited about it. We said, man, isn't this so interesting that you change the thermal regime of the floor plate, and suddenly, even though you're not melting, you're burying the building, and the resident is like, yeah, that's wonderful. Could you put my building back to the way it was before? It makes research an exciting place to be, but buildings are still for people. So we have to figure out how to deal with this. I remember I was pretty young in my career at this time, and I remember talking at a community meeting saying, this is a great shape, and we've done some vector analysis, and we think if we have this octagon-sized building, that it'd be way better from a snowdrift perspective. And an elder person in the community stood up and said, yeah, that's why we used to design our buildings that shape. That the local people already knew this. We have many generations of knowledge from a building physics standpoint. We don't need to reinvent things if we can remember them. And so I think, we can go back, everywhere in the world. This isn't uniquely northern. Everywhere in the world, you go back far enough in history, and a building was built by the person that was supposed to occupy it with a firm knowledge of what local materials were available, what building physics were relevant for their climate, and what the culture of the people that were going to live in it were going to need out of the building. The thing that's exciting about the Arctic is that wasn't that long ago. It's not like in certain places. So you can go to community meetings and meet people that have this memory of pretty exciting and ingenious understandings of building physics and use that knowledge. Next slide, please. So you can do this. You can get your anemometer. You can put your building on the site. You can use your software. You can get a windrows diagram. You can figure out what the vector analysis of snow is, and you can set it up. Next slide, please. Or you can do this. You can talk to elders. You can talk to people that live in the community. Everywhere in the world, old people sit around and talk about the weather. There's no place in the world where that isn't true, and Alaska is no different. So if you want to learn more about the weather patterns that are going to influence your building, community meetings and local, especially in either hunter cultures or farming cultures, people talk about the weather even more. We don't have much of a farming tradition in coastal Alaska, but we've got hunting cultures that are ancient. And so that discussion of site microspecificity is uniquely available to you as a designer. So if you go to a community to work, the best thing you can do is stay as long as you're budgeted and a little longer to talk to real people that live there, and your building is going to behave better. Next slide. And if we fail, it won't fail small. And so I think that's one of the problems is you're going to see if you grow up in the north, you grow up surrounded by building failures, partially because of our physical environment, partially because of the nature of colonialism and its history, partially because of the nature of what cultures look like when they crash together. We have a lot of failed buildings in the north, and so it can be a daunting and intimidating place to practice architecture. Next slide, please. The best thing we can do is listen. Stacey's going to talk with you tomorrow. She's an anthropologist. She's a good listener. I am not an anthropologist. I'm an architect. Learning to listen took some doing. You are not rewarded in architecture school for sitting and listening. So the way that our profession, our education encourages us to create our vision and build it take some re-education when we do community work, when we work with real people. If we work with people that aren't like us, that don't live in the same physical environment or cultural environment as us, it's a re-education that doesn't happen until you graduate. Next slide, please. Simple things like whether a house should be in the earth or on it. Simple things like whether every room in a house should be the same temperature. You know, whether you should have hallways. You know, I come from an urban context, not a big town, but, you know, an urban context. And I don't know, I have an idea of what a floor plan should look like. Some of the buildings that we've worked in, we've been instructed not to put hallways from bedrooms into living rooms. And this would seem kind of strange, you know, walking straight out from your bedroom into a living room with no privacy, but the idea or the cultural context was communicated to us in this particular project in Anaktuvik Pass was that it promotes family unity, and they didn't want people at the end. A lot of public housing, low income housing, has long hallways where family members isolate themselves from the family unit. Simple things that are different, that have nothing to do with building physics, and are an interesting part of the process. So getting time on site and hearing those things is more important than anything. Next slide. And those lessons that used to be there. This is a traditional dwelling on the top where they would have an elongated entryway, sometimes even with a cold trap, natural cold trap into the building in a very cold place. No one wants to live like this anymore. It's not like we want to live in sod igloos, but the idea of what an entrance should look like in a northern place, it should be long. There should be a grade change. You shouldn't, if you walk into a bank in the airlock, and by the time you get to the interior door, the exterior door is still open behind you, and all the air from outside comes in, and then basically you just air condition the hell out of it or heat the hell out of it with energy. This is not a northern approach to design. So these stubby little entries, they look like southern buildings to me, but they're out on the tundra. You see them everywhere. There are things we could do well to remember that we've forgotten about building physics. Next slide, please. And if we forget them, we live like square pegs in a round hole. You know, the idea that it's inevitable that the world is urbanizing has some truth to it, but it's not inevitable that the Arctic is better off from urbanizing if Arctic cultures are not necessarily prone to urban living, with some pretty ample literature to back up that it sometimes doesn't work out that for the best. Next slide, please. In the end, we make spaces for people. And if we make spaces for people that don't belong to the same culture or climate as us, we have to ask more questions. When they first started doing public housing in the north, there was a huge rash of plumbing failures because in marine mammal hunters, they'd be slaughtering fish and seals and whales in the bathtub. The bathtub couldn't handle the marine mammal waste. It would plug up, the bathrooms become inoperable. There are various ways to react to the problem of the seal in the bathtub. One was the governmental context, which was stop doing that. It's uncivilized. You know, that has never worked, ever. There's also the engineering approach, which would say, if my occupant is going to slaughter seals in the bathtub, then I'm going to design a more robust drain for a bathtub that can handle marine mammal waste so that they can live their traditional life paths and not break the equipment. That's an engineering approach. An architectural approach would be, I'm going to create a space in the house that's deliberately made for processing the animals that the people in this region process, and then they won't need to use the bathtub. They can use that for bathing, and that's an architectural approach. You might think that because I'm an architect, I think that's the best one, but I think the engineering approach is just as good. The only approach that we need to get rid of is the governmental approach, where we say, you know, just stop doing that. I think that's about all I've got today. We're going to talk a little bit about logistics, but I think I'd rather field questions because we're running out of time. So the only thing I would say about Northern logistics is that in architecture school, I was never taught to choose materials based on how they traveled to site. I was meant to choose them based on their appropriateness for structural loads or insulation values. But 40% of all construction costs in the Arctic is based on shipping. And so you've got to choose your materials based on how they get to site. The barge companies, the plane companies, they're smart. If it's bigger than it is heavy, they charge you by volume. If it's heavier than it is big, they charge you by weight. We have to think of ways to choose materials that can pack, that can ship, that can get to remote sites. And that creates a very different way of thinking about design. And you can skip to the thank you slide there. I think that's good enough. I was going to give a couple examples of that, but I'd rather field questions, I think.
Well, thank you so much, Aaron. This was an immensely interesting lecture I have attended in a long time. And it was full of surprises. I mean, I was not aware of these things at all, but well, this was like knowing how building science principles are completely different in northern region. And thank you for all the insights of it. And thank you everyone for joining. So if you have any questions, we can take them right now.
And please be sure to come tomorrow when my colleague Stacey Fritz will talk about engaging with communities in more detail.
Absolutely.
She's been doing it for quite some time, and we'll have some interesting things to say.
Hi, Aaron. This is Tarek Raka.
Hey, Tarek.
It's a really, really impressive lecture that I wish we were able to advertise for more and have much more attendance. So be sure to be on the lookout for us inviting you back to give a talk at Georgia Tech in classes that are relevant, because from a building physics perspective, there are so many lessons beyond just designing in the north. The main one that I would like to ask you about, your personal experience is, you said that if we, in one way, learn from our past or ask the right questions for elders or those who have the memory, like learn from our heritage, we would not be doing any reinvention or any invention because we've already figured it out. Can you please share with us not just the moment where you've learned this lesson, which seems to have a relationship with that town hall experience, but actually the people that you seek out to ask these questions, and what kind of questions do you typically ask? And I know that we're already over time by 5 minutes, so if that could be a question you entertain and then we conclude, that would be great.
Sure. Well, the truth is we need both, right, Tarek? We need memory, and we still need invention, because first of all, we don't necessarily want to live the same exact way as we did 1,000 years ago. We want improvements and we want invention. And also our world is changing so rapidly. There's no part of the world that is changing more rapidly than the Arctic when it comes to climate. We're warming faster. We started sooner. The problem is greater right now. So we need both. We need invention, and we need our elders and people that understand how we lived before. And I say we as Northerners. I'm not an indigenous person. I was born in Alaska, but my roots are on the Eastern Hemisphere. So I think when we talk to people, let's say, for instance, I know there's a project in Tyonek coming up, right? How do we engage people? First thing you do is learn about the land, but not necessarily just from NOAA, from the weather files, from your daylight files in your SketchUp plugins, but from standing there and listening to people talk about the way they view the land, because anyone that is in a long-standing community can tell me a lot about the land, but they can also tell me about their place in it, which is just as important when dealing with older cultures, with indigenous peoples. In Alaska, and this is not just true in Alaska, this is true most places in the Arctic. If a town is 100 years old, it was probably a good place to build a port. It was probably a good place to build a mine. It was probably a good place to connect a railroad. If a town is 1,000 years old, it was a good place to eat. That's how settlement occurred in older times. So listening to people talk about food security, about the way weather interacts with traditional life paths associated with that, why people live in a place, what brought them there. Sometimes it may be that they've been there since the 8th day and they know everything about it. Sometimes it might be that they were forcibly relocated there and there's trauma associated with where they are. You'll never know those things until you're a house guest and listen to the stories, you know. And if you're an architect, once you hear those stories, you're going to see it in the buildings everywhere. You're going to see it in the buildings that subscribe to it, and you're going to see it in the buildings that fail to recognize it. And because if you already have an architect or an engineer's eyes and you hear those stories, you're going to see it in the buildings. You're going to see it in the infrastructure. You can't help but see it.
Thank you very much. Really appreciate that response.
Well, thank you for having me. I hope you tune in to watch Stacey talk tomorrow. And I'll put my email in the chat. If anyone has other questions, you're welcome to. We're a nonprofit lab. We're here to help architects and engineers and students that want to practice design in the North. So reach out. Our purpose is to lend a hand.
Sure.
Thank you, Aaron. That was a terrific lecture. And glad to see you, and I hope to see you many times more.
I didn't get to see your face, but I knew you were out there.
Yeah.
Good to hear your voice. And thanks for staying up late, y'all. I know that it's only 4:20 here, but I know it's later down there.
Well, thank you very much, everyone, for joining. And please join us tomorrow as well. You already have the links, and you can also still share it with your friends if they want to join. Thank you so much for joining today. Thank you, Aaron. Bye-bye.
Thank you.
Bye-bye.